Okay, now this is working.
Okay, perfect.
Okay, so I'm gonna start out by asking my first question. This is the who, what, where, when, and why. So basically, that's just giving some general information on the topic. So, if an asteroid impacted the Earth, who would be affected by it?
So the question becomes, what is the size of the asteroid? So if we're hit by small particles that you can essentially consider to be a small asteroid all the time, and the atmosphere burns them up. So, but by the time an object is, say, a football field, you're going to have some type of global impact, right? That you'd have immediate death around the explosion, right? And then you would have a very hot material going into the atmosphere, and that would be kind of like a mushroom cloud. So then you could have a larger radius of people who would be impacted, like secondary effects, like falling ash, debris, material, right? But they still may be able to survive, right? But you'd still have some death. But then from like a much larger, like you say, continent or even global aspect, right? So you have food chain issues, you have medication issues. Like let's say, we have people that take insulin. What happens if we lose the main factory that produces insulin in that continent? Well, then now you don't have that. So all the roads would be destroyed. So it would be very difficult to get material from one side to the other. And so this material would then go up into the air and start blocking some of the sunlight if it's a large enough explosion or impact. So the question of who would be affected, everyone would be affected, but to a different level, right? You would either be dead, portion of the population would die in a larger radius, and then you would have global impacts that involve food, travel, transportation, medicine, healthcare, and that would have a global impact of everybody's day to day.
Okay.
And
Sure.
so if it's a small enough asteroid, it's going to have a very small impact. If it's a large asteroid, it's going to have a much larger impact.
Okay. So right now it's basically a question of size and where it hits.
Correct. Yep.
Okay. So my next question is, um, so like adding on to the previous question, in case an asteroid hits in a certain place, will the people within that vicinity be affected more than people out of that vicinity? Like, what would you say is like the range of effect?
So the range of effect, this is where we get very technical, right? It comes into things like what happens if an asteroid hits a cornfield in Illinois versus if an asteroid hits downtown New York City, right? So if a downtown New York City, obviously there'll be a lot more death because you have a higher concentration of population, right? In Illinois, like in a cornfield, yeah, there'd be some death, but the immediate impact to a large population isn't going to be there. So the people closest to the impact will have the greatest discomfort, the greatest impact of, possibly death, food, supplies, right? It's very much, if you think of like if a hurricane came through, right? If a hurricane comes up and hits Florida, the East Coast may get rain and severe storms over the following couple of days, but it's really the devastation is going to occur where the central impact, the central landfall actually occurred.
Okay.
Does that make sense?
No, this makes sense. Yeah,
Mhm.
I understand. Okay. So my next question is, I know that there are a bunch of asteroids out there which could have a potential impact, but in what time period will an asteroid impact happen?
So this question is a very statistical answer. So you can look at a size. So the two things to look at is what is the size distribution of the asteroid population that's near Earth, right? And essentially what it is there's a very low number of large asteroids, but
Okay.
there's a very high number, and it's almost like an exponential growth, a very high number of small asteroids. Well, our atmosphere protects us from a lot of the smaller ones. The atmosphere will just burn these up. And so when you start looking at the ones that we think could hit the ground, right, that cause massive damage, say 50 meters, or say a quarter to a half size of a football field, what you end up seeing there is, on average, you can assume at least a small impact once every 100 years, right? With a larger impact once every 10,000 years, right? And you can kind of scale this up and say like one global impact every 100,000 years or 100 or a million years, right? So how probability works is it doesn't actually tell you what is the probability of it occurring this year. It just says over the next, in 100-year time span, it should occur once, right? But it doesn't actually say in like 2050 it will occur once. It just says in this time frame we should at least have a moderate impact, a small to moderate impact. So to answer your specific question is the approach that NASA is taking is that if we can find and track at least 90%, right? If we find one that's going to impact that's large enough, we need about a 10-year lead time to then be able to do something about it. And so the approach is that from a statistical standpoint, we don't know when it's going to occur, but as soon as we can find it, as soon as we can track it, then we can do something about it. But until we know it's going to occur, we can't start planning for it.
Okay.
You can't start planning the specific mission to go tackle, to go handle it. So.
Okay. Okay. So my next question is, so like you said, they will start preparing 10 years before, but is there some kind of, is there a relationship between how long it takes to prepare and how big the asteroid is?
Yeah, so here's some of the science behind it. So we know Earth orbits in almost a circle, right? And we go around the entire, we complete a full cycle at once a year, right? The definition of year. Well, turns out Earth moves the diameter of Earth every 8 minutes. Okay, so if you have an asteroid on an orbit, right, that's going to intersect with Earth, you need to speed up or slow down that asteroid by 8 minutes, and that will take you from an impact to a flyby. And really, like say you have a direct impact, you only have to slow it down, say 4 minutes. So then if you say, how do you slow down an asteroid by 4 minutes in its orbit? That's a very difficult problem. However, because we're in the solar system and, essentially we don't have any atmospheric drag and stuff like that, if you can go to a really large asteroid and say slow it down like 1/100th or 1/1,000,000th mile an hour, right? And over time, that tiny slowdown in velocity will have a large impact in time. So the larger the object, the heavier it is, really the longer lead time you need to speed it up or slow it down. Whereas if it's a much smaller object and it's going to weigh a lot less, you don't actually have to have that much time to kind of change the have a large velocity change.
Okay. So how about in terms of ground control? Like in terms of ground control, like preparing the rockets and stuff, would you potentially need like would you potentially need a bigger spacecraft or a different approach to deflecting a larger asteroid than a smaller asteroid?
So one of mankind's limitations right now is essentially rocket fuel, right? It takes so much rocket fuel to get a pound of rocket fuel into space, right? And so we can't just take a whole bunch of rocket fuel right now, launch it into space, because you're going to burn a lot of the rocket fuel getting the little bit of leftover up into space. So NASA has a system they're building called the Space Launch System, SLS. And in theory, what they're doing is you can launch fuel tanks and then be able to connect those fuel tanks in space. So I say all of this because depending on, we know Earth's orbit, depending on the orbit of the asteroid, mankind may not have enough rocket fuel to reach the asteroid at any point in its orbit, where we may have to get multiple fuel tanks in space, connect them all together, to then be able to rendezvous with the asteroid to then start manipulating its speed. So yes, the larger the asteroid, the more potential rocket fuel you're going to need, and the less ideal windows potentially exist to kind of be able to move it.
Okay. So just one more trail on from this question.
Mhm.
So so in terms of building a rocket and a deflection system, is there a time difference in building a deflection system for a smaller one or a larger one?
Probably not, right? So the two things is that if we found an asteroid that was going to impact in 15 years from now, essentially what I believe you would get is you would get some of the world's best engineers who are already working on the problem, but you would get 100 times those engineers now all dedicated to the same project. And then you potentially are going to get multi-country, multi-coalitions all working together, putting resources together. So if we truly identify one that's going to show up in 15 years, I really think mankind will come together, and that although it'd be a much larger object or have a much larger scale operation, I think we would get the manpower to be able to handle it.
Okay.
So I mean, and it's one of those that you could imagine like Japan building a portion of it, European Space Agency, Russia, China. Like if everybody works together, not one country has to fund and build the entire operation, but essentially you can bring pieces in together.
Okay. Okay. So my next question is, so this is a bit of a general question,
Mhm.
but why are asteroid impacts a threat?
So, so are you asking why near Earth asteroids exist, or?
No, I mean like, why are they threatening to the planet in case they hit? Right, depending on size, like bigger ones can cause mass destruction, but then what about like smaller ones? Like maybe I'm about right, let's say 10 meters, 20 meters, around that size. Why are they a threat?
So, so it's one of those that the reason why the smaller asteroids are still considered a threat, like, so if you do like a risk analysis, the idea of a risk analysis is to look at how severe something is if it occurs, but also what is the probability or frequency of it occurring, right? So the asteroid population, like we had talked a few minutes ago, there's a small amount of big ones and a large amount of small ones. So although a smaller asteroid is going to have less damage potential, the frequency or the probability of occurring is much higher just because the population is so much larger. So we care about the small ones just because they have a much higher frequency of occurring, whereas a larger one has a lower chance of occurring, but has a really high damage potential.
Okay.
Right. So imagine this, like, is there a higher probability of getting in a car accident or an airplane crash? Right. Well, if you spend most of your days in a car, it's probably you have a higher chance in your lifetime of being in a car crash. However, if an airplane crash occurs in the air, it is extremely deadly, right? Like you have a good chance of surviving a car crash. You don't have a good chance of surviving an airplane crash, right? So it's one of those of what is the damage versus the frequency of occurring, and then that's how you kind of get like a risk assessment of what you need to actually worry about.
Okay. That makes sense. So my next question is, so I've seen people demonstrating in the lab what an asteroid impact would do to the surface of the Earth. So they might like replicate the surface of the Earth in an asteroid, and then they might replicate what would happen if an asteroid hit the Earth. So how exactly do you do that?
How you actually replicate it in the lab?
Yeah.
So turns out, if something is coming into the atmosphere, there's a concept called terminal velocity, which is essentially like the fastest an object can move in space or through our atmosphere, due to drag and all this stuff. So what some of the assumptions that you can end up making is that if you have a head-on collision with an asteroid, the atmosphere is going to rapidly be slowing the object down. So you can get a pretty good idea of the speed the object's going to hit the Earth at. Well, the other thing is in the size, and you get the weight, right? So, but mass times velocity is momentum. And so it's relatively easy to get in a momentum, an idea of what the momentum would be. And then it's one of those, you can compare momentum explosions to say like, a nuclear blast. We know how much energy like a grenade or a TNT, stick of TNT or stick of dynamite or a nuclear blast creates. And you can make those comparisons pretty quickly.
Okay. So what units do you use to like measure the damage? This is just a side question, but like what type of units do you use to measure the damage or the energy released?
So if you want to do energy released, you can basically, if you know the mass and you know the velocity, you can get energy out of that. If you want to know like the damage potential, like it then depends on how you're measuring damage. Like, is damage in death? Like how many deaths you have, how many square miles or square kilometers of land destruction, global impact. I mean, there's different ways to manage actually the damage effect, but on this specific, the energy release is relatively simple. If you have a mass times velocity and a mass times velocity, like two cars colliding head on, you can calculate exactly how much energy is there. And so if you know Earth and the mass of Earth, and you know the mass of the asteroid or comet and the velocity, then you can calculate that energy relatively quickly and pretty accurately.
Okay. So my next question is, so let's say, I wanted to replicate the experiment you do in the lab, or someone else wants to, but they don't have like expensive and fancy equipment. How would they be able to replicate the experiment?
See, that's the difficult part to do, because some of the NASA sites that are doing like micrometeorite impacts studies for like the space station, they have to get particles up to a really, really high speed to get some of the equivalent energies. And that's the problem. And that's the problem with asteroids, is that they're going to be moving so fast and be so massive that I don't think without like specialized lab equipment, you could actually replicate that. And so one of the things you find is that it's a lot easier to replicate in what we would call like a simulation, like a computer model, because then you don't need the high-end equipment. You need a computer, you don't need the high-end equipment to actually get the velocity, get the momentum up to the required level.
Okay, that makes sense. So my next question is, so I know, so like you're a planetary defense researcher. So as a planetary research defense, sorry, as a planetary defense researcher, do you feel like there's enough funding for asteroid deflection at this point?
So note that the NASA has funded what's called DART, the Double Asteroid Redirect Test. It's currently in flight, and we're going to, we have a main asteroid, and it's got a moon, right, orbiting around it. And so the mission is actually to go impact the moon, what we call the satellite of that, to then be able to understand, to start being able to study different deflection methods. So I would say, yeah, there's adequate funding to start doing this, but it's also one of those that there's funding right now to find and track the asteroids, right? If we ever found one that was going to come and impact us with enough lead time and be large enough, I think the funding would would quickly arrive to then start building a much larger coalition.
Okay.
But again, it's one of those of, it's hard for me to say that planetary defense needs more funding, and that funding needs to be taken from someplace else, right? I mean, there's NASA administrators and much smarter people than me doing accountant work to try to make sure that all the areas of natural disasters and planetary safety are adequately funded. So yeah, I would say there's more funding is always wonderful to have, and you can do more work. But it's also one of those, I think it's the responsibility of the scientists to make sure that they can do their work inside of the funding that's allocated.
Okay. So my next question is how much effort is NASA taking to actually, prevent an asteroid impact? You said DART, but are there any other missions? Are there like real time, deflection simulations and stuff going on, or like scientists making breakthroughs and stuff?
Yeah, so there's an entire group. Give me 1 second, I'll look up her name real quick. Yeah, there's a woman named Jessie Dotson at NASA, and her and her team is absolutely wonderful, and they work extensively trying to build simulations for how the asteroid, like if we see, there's multiple different types of asteroids. You could have metal, rocky, stuff like this, right? Of how that asteroid would come through the atmosphere, how the atmosphere would actually slow it down, the impact, where if we give her essentially an orbit where it's going to intersect with Earth, then she can start doing all the damage modeling ahead of time. And so that's one of the really big new areas that to me, it has had so much breakthroughs, because now we can fairly quickly, I'm saying within days, go from we're going to have an asteroid impact to immediately knowing what potential damage we're dealing with. And that's pretty powerful. So that's a big breakthrough. The other one of the other breakthroughs that we're really talking about is how to rapidly get more information about an asteroid. And so when we detect its orbit, we don't know what it's made out of. And so there's a lot of different telescopes that we can then utilize to try to get like surface composition, spin state, how is it rotating? So a lot of that kind of information is and bringing it all together rapidly. I would say that's the other big breakthrough that has definitely happened over the last few years.
Okay.
Because you have all these different teams doing a slightly different work, and how can you rapidly bring that together to kind of make a conclusion about what the object is?
Okay. So, yep. This is actually pretty cool what they're doing in the lab.
Mm-hmm.
Yeah. So, just one side question. So, how many asteroids are being discovered per day?
So there's a difference between asking how many asteroids in the solar system are being discovered a day versus how many near-Earth asteroids are being discovered. So right now we're discovering around 3,000 near-Earth asteroids a year. However, in the main belt asteroid population, we're not really discovering that many more, but that's more due to the limitations of the telescopes that are searching for them. And so there's a couple new telescopes coming online, like the LSST Rubin Observatory in South America, that will be able to discover quite a bit more. So right now we know of about 1.3 million main belt asteroids and right around 30,000 near-Earth asteroids.
Okay. Sure. So, do you feel like more space telescopes needs to point at asteroids? Because lots of asteroids don't reflect light from the sun as we see it from Earth. And so those asteroids, if we don't identify them, they could have a potential threat to us. So do you feel like we need to point space telescopes more at asteroids?
So here's the big challenge of space. So there's a lot of pluses to space. So for instance, if you're using a visible telescope, as you know, you need the skies to be dark, right? If you're using a visible telescope from the ground, you need the skies to be dark, so it's got to be nighttime, but you also need clear weather, right? So you're going to be cloud dependent. So we put telescopes on the top of mountaintops because it helps us reduce atmosphere, and ideally we're putting them in places with a lot of clear nights. So they're easier to operate and fix because they're on the ground. And so you can have a much longer lifetime. However, the advantage of space is that you don't have to deal with atmospheres and you can always have clear skies. However, the problem with Hubble, Hubble's wonderful, but because it's in an Earth orbit, you essentially get 90 minutes of observing, 90 minutes where it's essentially on the sun side. And so for asteroid discovery, you need a huge field of view. And so there's new space missions that NASA has funded, like the Near Earth Object Surveyor. It's going to go to one of the Lagrange points, which is kind of like a gravitational saddle, but it's going to go inside of Earth's orbit looking outward. And it's going to then be able to look in front of Earth and behind Earth's orbit, essentially every 14 days, switch back and forth, and be able to scan a pretty large area of the sky. The other thing is, instead of it being an optical telescope, you're absolutely right, asteroids don't emit light. The sunlight is either reflected back to Earth or it's absorbed. Well, as an asteroid heats up, it's going to emit in the infrared. And so the Near Earth Object Surveyor is actually an infrared telescope, so it's going to look for heat signatures. And so that mission, I think, is currently planned to be launched in 2026. So I don't know how many more space missions we would need to be able to find these, because NEO Surveyor should do a really great job of being able to get us to that 90%. I think in 5 years, they should get us to that 90% mark of discovering 90% of the near Earth asteroid population.
Okay. So as of now, how many asteroids are there to discover? Like as a percent, or as you could put a number on it, but how many asteroids are left to discover?
You mean in the near Earth asteroid world?
No, any asteroids, main belt or near Earth.
So in the near Earth side, we somewhat consider there's 100,000 near Earth asteroids that are dangerous to us, and we've discovered around 30,000 of them. So in the main belt, because those asteroids are so much farther away, we can't see the smaller sizes. So I would say there's probably 10 million is probably a safe bet of main belt asteroids of a size that we would need to be concerned with. But if the main belt asteroids are in a stable orbit, not until they become unstable do we need to worry about them.
Okay. So this is my last question. Could we use radio telescopes to discover asteroids, or to at least find and observe asteroids?
Okay, so two things. So let's talk the discovery side. Do asteroids emit radio waves?
I think yes, because when they heat up, infrared light is far more high frequency than radio light, and so I guess that it's going to emit a lot in radio too, because if it emits if it reflects an infrared and optical, why not radio?
So so with your theory that it's going to reflect radio waves, then you're also under the assumption that the sun is emitting radio waves.
Well, I'm sure that the sun emits at least some radio waves, probably a lot, because radio waves are really easy to produce.
So the reality here is that a radio wave is, since it's so long, there's actually very few coming from the sun that you can actually detect with a radio telescope. And so asteroids are considered radio quiet in the radio wavelengths. So we do use radio telescopes, but what ends up happening is to observe asteroids. But what happens is you have to use two telescopes. One telescope sends a signal to the asteroid, so you have to know where it already is, and then the reflection is then picked up by a second radio telescope. And so we can get really good shape modeling via radio telescopes, but you have to know where the asteroid already is to a very high precision.
Okay.
And so, it's due to because essentially the asteroids aren't bright in the radio.
Okay.
And so then that leads then to the discovery part, is that it's extremely difficult for the discovery, mainly because you would have to have two telescopes, one kind of like shooting radio waves all over the place, waiting for a response. And so the radio side is excellent for getting us shapes and rotational rates and spins and like getting really cool images of the asteroid, but it's going to be very poor in discovery and kind of like follow-up.
Okay. Sure. So that makes sense. So I'm gonna stop recording here.
Okay.